second. I thought maybe the talks were today. Everybody was in the room. So weird. Why did they show so late this class? It's in, yeah, it's in Corey, but it's fifth floor. Yeah. Good, man. How you doing? You good?
Okay. Let me get started. Let me first start taking care of some logistics. Okay, so the presentations on Friday from 9 to 11, Wang Room, which is the fifth floor of Quarry Hall, in front of the elevator. Okay. I received, I think, email from a lot of you. The only one whose name I have a question mark is Howard. Are you doing a project or a literature review?
Yeah, I was actually originally doing a literature review.
Uh-huh.
I wanted to also present something along with that.
Okay, so a project.
Yeah.
Okay, so then based on that, the total number of presentations are 10. And let me write down who those are. Um, I won't write it now, I'll just read it. So I got Jimmy Wang. Is he here? No, but he mentioned that it's a project. Robert Held. That's you, right?
Yeah.
Okay. Casey, who's not Casey, sorry, is not doing anything. He is attending a conference. Howard, Chris Anderson, Alan, uh, Prasant Jivan together with Patrick Garg together with David Lin, and then Sergey together with Min together with Mary, and then VJ together with Galen together with there's Eric Battenberg. I don't have his name down here. So together with Eric Battenberg. So those are the groups that I have, or the individuals. There are four names that I don't have any information on. Two of them are from nuclear engineering, two of them from mechanical engineering. Specifically, I have Shiman Jiang from nuclear engineering. Is he here? Mingshan Sun from nuclear engineering. That's you. Are you taking the course for credit?
Yes.
And are you having a project or a literature review?
Project.
Did you submit a proposal?
Yes, I did.
Okay, and what's your project on? What's your project on?
It's on spectra detection. Nuclear medicine.
Okay. So I didn't read your name. So you will be giving a presentation.
Okay.
Okay, so Howard is with Howard we had 10, and with Mingshan we got that's 11. Okay. And then Shuan Fan, mechanical engineering. And then Shisheng Zheng, mechanical engineering. So okay, so I assume those guys are not in. So let me just do you guys want to come up with a tentative order that you give your talks? By any chance? Okay. So roughly, let me just calculate. We will do the ordering in real time in the class from 9 to 11. But roughly speaking, I have let's see.
These are on a group of similar length, maybe.
Yeah, I don't want to spend time to do that. I'm trying to count the number. So Jimmy Wang, Robert Hill, Howard, Chris, Alan, Prasant and the team, Mingshan, Katrik and the team, Sergey and the team, and Galen Reeves and the team, and Samuel. Did I miss anyone? So I think it's 11. Okay, so we have 11 presentations, and we have 2 hours, and we have 3 multi-person projects. So I was just going to give a little bit more time to the multi-person presentations than the other ones. So 2 hours is approximately 120 minutes. Yeah. So 120 minutes divided by 11 projects. So yeah, we'll just give a little, a tiny bit more uh, to the multi-person projects. Let's stick to 10 minutes. 10 minutes per project presentation. Okay. So that'll take us to 110 minutes, and and then we have 10 minutes for question and answer, for slipping, and various other things. Okay, question.
So we should just like email ourselves the talk to us from your computer and then like
Yeah,
send it out.
yeah. But if you're showing video, then that's more problematic. It's better to bring your laptop. I don't think many people are showing videos, are they? Okay. Any other questions or comments? Okay, very good. And actually, what I'd like you all to do, that's another important thing, is I want you to bring along a hard copy of your presentation. And I don't know, make 15 copies of it. But it doesn't have to be one per page. That's pretty wasteful. You can do 4 per page or 2 per page, something like that. Um, of, actually, is that overly imposing on you guys? Is that difficult? Just tell me if it is. I won't hold it against you if you tell me that's a pain in the neck. Don't ask us to do that.
Can we just put it online afterwards?
Okay, no, I want one copy at least for myself. Let's just do that. That's a good intermediate solution. Bring along one hard copy of your presentation, because I want to make comments and notes on that and pass it along to you and pass it and keep it for myself. So bring one copy of my PowerPoint, and then later on you can email it to me. One hard copy of your PowerPoint for instructor. Okay, and then obviously the papers or the reports are due on May 15th. Okay? So then in that one hard copy, do make it one page, one per page, so that I can write comments as you talk, so that at the end of your talk, I can then say, okay, here, 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 comments, feedback, questions, whatever. Okay? Any other questions or comments? All right. So let me backtrack as to where we were last time. We talked about JPEG and we talked about discrete cosine transform and ways that one could quantize and and uh, and use DCT together with Huffman codes and various other things to do still image compression. What I'm going to talk about today is multi-resolution coding and subband coding and wavelets. All of those are interrelated kind of topics. And I will begin by talking about what's called pyramid coding, which was introduced by Burton Adelson in the 80s. Then I will move on to talk about subband coding, and then from subband coding, I'll proceed to talk about wavelets. So wavelets have been around since late 80s, and if they've been connected to different and related to different disciplines by various people. And indeed, in the signal processing community, people had been doing subband analysis and subband coding for a long time. And so when wavelets were introduced, the reaction of that community was, oh, wow, we've been doing that for a long time. And the reaction of computer vision community was, oh, we've been doing multi-resolution analysis for a long time. But basically, what happened was Stefan Mallar put the concept of wavelets into a rigorous mathematical framework. And then I'll talk a little bit about quantization and coding of wavelet decomposed images, because I think that's just as important as the decomposition. Remember, the 3 basic questions that we deal with in compression is what to code, how to quantize, and how to do bit allocation. So for the problem of what to code, we've talked about we could code pixels in the spatial domain in a predictive way or a differential way, whatever. Or you could code DCT coefficients. Or now, today, we're talking about the third technique, which is wavelet. I can code subband coefficients or wavelet coefficients, etc. And for DCT coefficients, we've already talked about quantization and bit allocation. We've decided we're going to be doing uniform quantization, but using perceptual cues and human visual characteristics, we might want to apply different quantization step size to different coefficients of DCT. And then for bit allocation, for those, we've decided to use Huffman coding. So that is a combination of those three things: DCT coefficients, uniform quantization, but with different step size for different quantization, with different coefficients, and Huffman coding. That's a bundle that defines JPEG baseline system. And today we're going to talk about wavelets, quantization of wavelet coefficients, and we'll see in a little bit that one of the most popular techniques for doing bit allocation for wavelet coefficients is arithmetic coding. Um, so so these are all kind of interrelated, and combination of these three things make up a compression package. Just a few words about, I mean, if there's a little bit of time, I talk a little bit about video compression. Basically, in video, what you try to do is combine some of these techniques. Essentially, you remove the redundancy between successive frames by trying to predict a frame from the previous frame using a series of motion vectors. And then, so then from that point of view, it's a predictive technique. What to code is the error of that prediction between successive frames. And then how to code it, people have applied DCTs and wavelets to that, the same way as they apply DCT and wavelet to regular still images. Okay? So if there's time, I'll talk a little bit about one of the fundamental ideas behind video compression. So let me start talking about multi-resolution coding, and in particular pyramid coding. I'm going to use pictures from both Eennlb and also Gonzalez and Woods. Okay, so let me number the pages really quickly. Okay, so multi-resolution, subband, pyramid, wavelet coding. All those in one shot. Okay. So I'm going to start by the notion of pyramid coding. And before I even do that, we've already to some extent talked about multi-resolution. Let me just explain what the word multi-resolution means. We talked about it a little bit last time. It essentially means looking at the same picture at different resolutions, different number of pixels. It could be different spatial resolution, or it could be different temporal resolution. So if you're talking about video, it refers to, for example, having different frame rates. That generates a multi-resolution temporal video sequence. If you're talking about still images, it just talks about number of pictures, number of pixels. We can switch to the screen on the computer for just a second. This just reminds you what we mean by multi-resolution. So this picture has been coded at 3 different spatial resolutions. So this is a multi-resolution kind of an image. So initially, as I said earlier, this notion of multi-resolution was introduced by Bert and Adelson. And it was in 1986 or so. And interestingly enough, when their paper got reviewed, um, this is one of the comments that the if you can still switch to the screen one more time. This is the comment that the reviewers um, uh, said about their paper. They said that this manuscript is okay if compared to some of the weaker papers. However, I doubt that anyone will ever use this algorithm again. So this was in 1982, and by far that whole concept of multi-resolution is one of the most powerful techniques today, 2002. So don't get discouraged if at times you submit a paper to a conference and you get discouraging comments like that. Okay, so so the reviewers of 1982 paper for these guys are very negative. Okay. Nevertheless, these guys kind of pushed forward, and their main motivation was they were trying to compute the motion correspondence between successive frames of video. And by the way, uh, Adelson is now at MIT, and I don't really know where Bert is, but Adelson is in the psychology department at MIT, and I think the work might have been done at MIT, but although I have a hunch it was done in Sarnoff labs, or maybe Adelson at that time was in Sarnoff labs. But their main motivation was they had successive frames of video, and they wanted for every little block in this picture, they wanted to find out where it came from in the previous frame, and it was just taking too long to do that. So the idea was, if you come up with multi-resolution representation of both images, so and you have n by n version of this image and n by n, and instead of solving the correspondence between the two n by n pixel images, if I now come up with n over 2 by n over 2, and then n over 4 by n over 4, and n over 8 by n over 8 versions of those pictures, and if I solve the motion vector estimation problem on top of the pyramid. So here I'm building a pyramid. That's why it's called the pyramid coding technique. So if I build a pyramid in this manner and I solve the correspondence problem on top of the pyramid by finding the motion vectors between n over 8 by n over 8 pictures, because it's much simpler, there's fewer pixels and faster, etc. And then when I get that rough estimate of motion vectors, I'll just keep refining it as I come down the pyramid. So their main motivation was purely a computational one. Then by the time I get to the bottom of the pyramid, then I have found my motion vectors, but I've done it in a much in a kind of a coarse to fine scale, and now I have the same answer. It might not be the exact answer I would have gotten if I did exhaustive search on the n between the n by n pictures, but it's close enough. Okay, so the initial motivation for these guys was to build, to compute a reduced complexity of motion estimation. So as I said, the basic idea was you have two n by n images, and you build a pyramid, n over 2 by n over 2, n over 2 by n over 2, and let's say n over 4 by n over 4, n over 4 by n over 4, and you do the matching between these guys first, and then you propagate the motion vectors down, and then you propagate the motion vectors, refine the motion vectors as you go from here to here, etc. So the question is, how do you build these pyramids? Well, if right off the bat, when you look at this picture, you would say, oh, what I have to do is probably just subsample this image to get n by n image to get the n over 2 by n over 2 image, right? And that's probably correct, except that what's wrong with that? What's wrong with that approach? Well, if I just subsample an audio signal, or if I just subsample an image, what happens? You get aliasing, right? So instead of doing just subsampling, what do I have to do before subsampling? Low pass filter to get rid of aliasing. So the question now we're going to address is how to build pyramid. And this pyramid that these guys built is more or less the same pyramid as we built for pyramid coding. They're kind of the same idea. So the basic idea is really to do successive low-pass filtering and subsampling. So what do I mean by that? Well, I start with this signal f of n1 and n2, and I do low-pass filtering on it, and then I subsample it. And this I call f sub I, and what comes out is f sub I plus 1 of n1 and n2. So as I keep subsample, as I keep subsampling this thing, I'm traversing up the pyramid, right? So in this picture, this is probably f naught, this is f1, this is f2, because I low pass filter and subsample to get this one, low pass filter and subsample this to get that one. Okay. So how is the well, subsampling? So this shows the process of generating the I plus first level from the ith level. Okay. So how do I do the filtering? Well, you can do any kind of filter that your heart desires. The f sub il means the low pass version of n1 and n2 is just fi, the image at the ith level, just convolved with some filter h of n1 and n2. We generally want to do FIR filters because we are interested in linear phase, and it's easy to design FIR filters with linear phase. So that's it. So the subsampling, that's pretty straightforward. We say f sub I plus 1 of n1 and n2 is just f sub I of L n1 comma n2 for n1 and n2 in the range of the image. We call it 2. Let me write down here. For n1 and n2 in between 2 to the m minus 1 and 0, where this m is the mth level of the pyramid, okay, and it's 0 otherwise, okay. And what filter I use here, what h I use, basically determines the kind of pyramid. So this h guy, if I were to use my red pen here, determines the kind of pyramid. Okay. So in particular, if I use, I can build a what's called a Gaussian pyramid. If I use the following separable filter, h of n1 and n2 is h of n1 times h of n2, where h of n, I approximate some sort of a Gaussian. Let's say it's equal to a when n is equal to 0, it's equal to 1 over 4 when n is plus or minus 1, and it's equal to 1/4 minus a over 2 for n equals plus or minus 2. And usually people pick a between like 0.6 and 0.3 or some number like that. Okay. So let me just for sake of completeness show you an example of a set of images that we will get if we do that, a set of Gaussian pictures in a Gaussian pyramid. That's figure 1036. So let me just show two things. Can you zoom in, please? Actually, zoom out. Just a tiny. Okay, great. So this is the h of n when a is equal to 0.3. It's kind of more flat-looking Gaussian. This is for h of n 8.4, 0.5, and by the time you get to 0.6, it's kind of more narrow. And this kind of shows the one-dimensional graphic representation of how we build this Gaussian pyramid. Okay, so at the bottom you have f naught of n1 and n2. If you can zoom in now for this bottom picture, that would be great. So down here you have f naught of n1 and n2, the pixels, and at this level you have f1, and this one I have the f2. So these, um, for the case that your h of n is 4 points long, you have these 4 points linearly. Well, actually, there's a 5 points. And look at this picture: 1, 2, 3, 4, 5. So these 5 points contribute to this signal, and then these 5 points contribute to this point, etc., etc. So you're building a pyramid by combining the pixels in that way. And if you start with the actually, I don't know the name of this picture, but it's not the Vegas. Okay, some other lady picture. 512 by 512. And if K is 4, that means you built 4 levels of your pyramid. So this is what you get this is the Gaussian pyramid that you get. So this is the 0th, F0, F1, F2, F3, and F4. Okay? So, so let me just quickly write down here, show figure 10.34 to 10.36 of Eennlb. Okay. And so now the question is, how do we apply this concept to pyramid coding? Okay. So get a fresh sheet here. Great. So how we do pyramid coding? Okay. So basically, the main idea is that you want to code successive images in your pyramid down from top to bottom. Okay. So the basic idea is essentially to code successive images down the pyramid from the ones above it. And use some sort of a fancy technique. So in other words, let me come back to this picture here. So essentially, somehow code the picture on top of the pyramid, the n over 4 by n over 4, either DCT or whatever your favorite technique is. And then once you've coded that, try to use the coded version of this top signal to code the next one, and then try to use this in order to code this one. Okay, so it's kind of a it has a kind of a domino effect from top. Start from top, code the top one, and then use successive levels to code the ones below it. Okay, so how do we do this successive thing that I'm talking about? Well, you interpolate the I plus f of I plus 1, the I plus 1th level image, in order to come up with a prediction for f sub I, and then code that prediction, subtract that prediction of f sub I from the actual f sub I, and that comes to generate what's called prediction error, and then code that prediction error using whatever favorite quantize and code it using whatever technique that you have, so that send it to the receiver so that the receiver can use that error. The receiver does the same thing essentially. The receiver receives that error and tries to build the FI level, and just keep doing that until you hit the bottom. Okay, so here code the so the basic idea is that you interpolate f of I plus 1 of n1 and n2 in order to get a prediction for fi. So this is the top, this is higher up than this one. Okay, and then so basically the prediction for f sub I, this is prediction for f sub I is given by the interpolated version of um, f of I plus 1 and 1 and n2, and you can use linear interpolation, nonlinear interpolation, or any fancy scheme that you want. And then code the prediction error. So EI of N1 and N2 is just the actual signal at the ith level minus the prediction that you came out with it. And this is really the story of our life in all compression schemes, is make a prediction, try to make that prediction as good as possible so that the energy of this error signal or the variance of it is small, so it can be coded with very few bits. Okay, and then you just repeat the above process until the bottom level image is reconstructed. Until the bottom level image is reconstructed, i.e. the original. Okay. So in this scheme of things, the sequence f sub I is called the Gaussian pyramid, which I already showed you, and this sequence e sub I of n1 and n2 is called the Laplacian pyramid. Okay. So let me just, for the sake of completeness, show you the a picture from figure 1038, which is an example of a Laplacian pyramid, just so that you know how these E signals look like. You can zoom in, please. Okay. So this at the bottom, I know it's very small. You've somehow coded the top level image using any kind of an intra-frame coding scheme. Then you interpolate that, subtract it from the next level signal, which is this signal here, and you get this error, and then keep on going until the final error that you have is this. So you have to code these error signals, this error signals, this error signal, and this error signal. Is that clear to everyone how it works? Yeah? And so right off the bat, what's one of the difficulties or disadvantages of this pyramid coding technique? Anyone? How many pixels did we start off with? This Leno signal, whatever we want to call it. It had this many, right? It was 512 by 512 originally. How many error values do we have to code now? Well, there's 512 by 512, 256, 128, and 64 by 64. So the total number of pixels that we have to code has been increased. It's true they have smaller variances, they have less variance, and therefore it takes fewer bits to code each of these pixels than the original. But the sheer fact that the total number of random variables we have to code has increased is a bad thing. Remember, in transform coding, that was one of the best advantages of transform coding, is that it has that compaction property. You have 64 pixels. By the time you transform it into DCT, you won't really have to code 5 or 6 of them. That's awesome. You can just throw away 59 or 50 or whatever, a huge number. Here, it's kind of gone the reverse. And that's exactly why pyramid coding is not used today. It's a basis for what came after, which is subband coding and wavelet, and which I'll talk about in just a second. But per se, it's not a very good coding scheme. And just so that you can be aware of this, this is the example of the coding that 512 by 512 image at half a bit per pixel, which is very high. I mean, I've showed you last time color pictures using JPEG 2000 that were like 0.1 bits per pixel. So to wrap up this discussion, I'd like to just show the flow diagram of this technique. If you can zoom out just a little bit. Okay, can you read those? I guess a little bit. It's not too hard. I mean, these boxes are interpolations, and so what you start is you start with. So how do we build this Laplacian pyramid? How do we generate it? Well, we've built the Gaussian pyramid, and this is our by subsampling subsample filter, subsample filter, subsample filter, subsample filter, just to get to the end of it. Now, at the end we're going to code this thing and send it somehow to the receiver. That's the F sub k. This is the kth level of the pyramid. That's the top of the pyramid. So you start from that F sub k signal, you interpolate it, right? And because you also add, so this is the prediction for F sub k minus 1, and then you add to it the error signal that you generated at the encoder to make sure that the prediction together with the error signal now matches the k minus first level of the pyramid. And I repeat this process until I get to F2 and then F1, and then this error gets added up and I get F0. So what it takes is these error signals need to be sent from the sender to the receiver so that they can both successfully in sync reconstruct this F0 signal. Okay. I wish that Jay Lim's book had these the encoder side, but it hasn't come. But it's pretty straightforward. Okay. Next, any questions on pyramid coding? Okay. So let me show you one other example of pyramid coding here. Not here. Yeah. I'm going to show figure 7.2. Oh, I'm afraid I have to download this. Let me just quickly do that. What's it called? Digital image processing. What's the publisher? Prentice Hall. Let's just add one more. I want it to take me to the book site. Oh, I misspelled. Oh, God.
Click on that.
On what? Oh, my God. You got it. Thank you. So let's just quickly download the faculty and then instructor's manual, PowerPoint presentation, and we want chapter 7. I forgot to put it on my own website, so we just quickly download it here. The funny thing about Google is that even if you misspell, it comes up with 1,000 answers of the misspelled thing. Sometimes, and the only way to know it is you say, oh, I know that topic should have raised, 100,000 answers. Why is it only giving me 5? And those 5 are all misspelled too. Okay, so if I go to figure 7.1 and 7.2, I can show you. Okay, so this is an image. This is how we build the pyramid. We already talked about that. And this is the pyramid representation of that original image. It's the vase image. Or how do you say it in American English? Is it vase or vase?
It's still vase, I think.
It's vase? Okay. So this is the Gaussian pyramid, and this is the Laplacian pyramid at the end. And okay, so now let's switch gears and talk about the subband coding. So how does, if you can zoom out just a little bit, so how does subband coding work? Sorry, can you shift a little bit? Thank you. Well, the idea again was introduced many years ago in the speech world, right? For example, where's this other PowerPoint? So, for example, if I go to if I look up the speech literature, I think it's Esteban. That's right. Esteban and Galland and Crozier were the first guys. So it was initially introduced in speech coding, and by these, I think these guys, French guys, Crozier, Esteban, and Galland. It was in 1976, so nearly 30 years ago. And the basic idea uh, is to start with your signal x of n and pass it through two filters, h naught of n and h1 of n. Subsample both of those. Once again, you can see very similar to pyramid coding. But here, you not only, so H naught is kind of a low pass filter, H1 is kind of a high pass filter, so you're dividing into two bands, right? But you can see that because we're subsampling both of those by a factor of 2, there's no expansion of the number of samples, okay? So one thing about pyramid coding that I forgot to write down, but we talked about it, is there's an expansion of the number of samples one has to code. Here, there's no expansion. So subband, no expansion on the number of samples. So then you quantize and code this and somehow send it across to some sort of a channel. And then at the other end, you upsample it by a factor of 2. And then pass it through signals G naught of n and G1 of n, another set of filters. And out comes a new signal, which we call x hat of n. Okay? And we're kind of hoping and praying that x hat comes very close to x0. X hat comes very, very close to x. Okay? And you can roll up just a little bit. And intuitively, the basic idea is that, roughly speaking, well, you can already see how the system would work if H naught was a brick low-pass filter and H1 was a brick high-pass filter, right? From a spectral point of view, you start this signal, you decompose it into low-pass component, high-pass component. Now you can downsample without introducing any aliasing. Now you upsample it, and then you pass it through some other filters, and you can get perfect reconstruction. Now, the beauty of subencoding is that these H naught and H1, nor G naught and G1, they don't have to be brick anything. You can have filters with smooth roll-off and still do a fairly good job. So I'm going to plot that. So if I were to plot magnitude of H naught of omega or a magnitude of H1 of omega, it's going to be something like this. This is 0, pi over 2. It's going to be something like that. Okay? The middle point is pi over 2. So this is H1, and this is H naught. Okay? And this is the low band, and this is the high band. Okay? So let's do a little bit of analysis, or just write down the expression relating the Z transform of this signal or to this signal. And we already know what happens to the Z transform of a signal when we subsample it. We know what happens to the Z transform of a signal when we upsample it. All of those we remember from the beginning of the course, or E120 or E20, etc. But the bottom line, after a bit of an analysis, what we can show is that x hat of Z, the Z transform of this signal, is given by 1/2 of H naught of Z times G naught of Z plus H1 of Z times G1 of Z times X of Z, plus 1/2 of H naught of minus Z G naught of Z plus H1 of minus Z G1 of Z. All of that multiplied by X of minus Z. This thing multiplied by X of minus Z. So So this term here is called the aliasing term. Why? Because it has something times x of minus z. Therefore, in order to generate what's called, in order to cancel aliasing, we have to make sure that our filters satisfy this condition where this thing inside this square bracket is equal to 0. Okay? So let me write that down. Let me roll up a little bit. Okay, therefore, to cancel aliasing, we must have essentially h naught of z times g naught of z plus h1 of minus z times g1 of z equals to 0. Furthermore, if I wanted x hat of z to be perfectly equal to x of z, this whole term inside 1/2 times this thing, this term inside should be equal to 2. Okay? To get what's called perfect reconstruction, we must have the following. We must have this guy h naught of z times g naught of z plus h1 of z times g1 of z equals to 2. So it's possible to write these things as matrices, and in other words, you can define this matrix H M of z such that, okay, so if I define this, let me just do that. This guy H M of z, a matrix made of H naught of z, H naught of minus z, H1 of z, and H1 of minus z. I can combine these two conditions as a matrix equation, and I can say that to get aliasing cancellation, let's just say to cancel aliasing and achieve PR. PR doesn't mean public relations, but just perfect reconstruction. We must have the following matrix equation: g naught of z, g1 of z, this two-dimensional vector, times this hm guy has got to be equal to 2, 0. 2 because of this and 0 because of that. So it turns out people have spent a great amount of time, energy, and resources in order to come up with conditions that these filters that have to satisfy for these to hold true. And in the signal processing literature, it's referred to as filter bank. Okay, why is a bank? Because there's 4 of them. There's G naught, G1, H naught, H1. So there's a lot of stuff going on. And one of the things that, before I go on about, so basically, let me just give a preview of what's coming. There's 3 broad categories of design techniques people have come up in order to satisfy these things. One is called QMF, quadrature mirror filters. The other one is called CQF, conjugate quadrature filters. And the third class is called orthonormal. And I'll talk about each one of those in just a second. But before I do that, I want to say one more thing about this set of conditions. And that is, if these conditions are satisfied, then we can show that the analysis, but let me first introduce the term analysis and synthesis. So in this diagram here, these filters are called the analysis filters, and these H naught and H1 and G naught and G1 are called synthesis filters. So what we're going to show is that for these analysis and synthesis filters to satisfy these conditions, the aliasing, cancellation, perfect reconstruction, they're going to be satisfy the biorthogonality condition, and I'll tell you what that means in just a second. So So H naught and H1 are called analysis filters. G naught and G1 are called synthesis filters. Okay, and we can show that if let's call this star, this equation star. If a star is satisfied, then analysis and synthesis filters are orthogonal. And what I mean by those is that the inner product between hi of 2n minus k, comma gj of k is equal to delta of I minus j, delta of n, for I and j being equal to being 0 and 1. And the inner product is just defined as this thing is just defined as the summation of h of over k of hy of n 2n minus k gj of k. That's the inner product just means this summation. So this is called the biorthogonality condition. Why is it called biorthogonal? Because there's two functions we're talking about, h's and j's, right? So that means the only time this inner product is non-zero is both the case where I is equal to j and n is equal to 0. Okay. Okay, so now having said that, let me now talk about the three cases of well, before even doing that, let me just talk about some famous examples of two-channel filter banks with perfect reconstruction, and then I'll talk about the three classes. Can you roll up, please? Okay. So here's an example of a two-channel filter bank with perfect reconstruction. So at the surface, you might say, "Wow, this thing is impossible." And so the low-pass filter, I'm going to use minus 1/4, 1/2, 3/2, 1/2, minus 1/4 for my analysis filter. And this is the tap coefficients. This is an FIR filter. And for my high pass, I'm going to use minus 1/4, minus 1/4, sorry, minus 1/2 and 1/4. And for my synthesis, can you roll down, please? My low pass is 1/4, 1/2, 1/4, and my high pass is 1/4, 1/2, minus 3/2, 1/2, and 1/4. Okay. So this set of filter banks is referred to as the biorthogonal 5-3 filters. It's called 5-3 because it's got 5 taps here and 3 taps here and 3 taps here and 5 taps here. And as you can see, these are highly related to each other, and that's not by accident. We'll show in just a second is the way to build subband filters. That's kind of the way to do it. And this guy Didier Ligal, who was at the time he did these, was a researcher. Can you roll down, please? Was a researcher in, but then later on he founded C Cubed, which is a LSI, which is a VLSI company building MPEG chips later on in the valley. He put patents on these things, and these are, which was kind of at the time it kind of was ridiculous, but it ended up being an important patent, and it was enforceable. Why did he put patents? Because these have low complexity, they have few taps, and they have very simple coefficients. 1/4 and 1/2 are very easy to multiply because it's just a shift to the left, right? in any event, just so that you can see what they look like, let me show you the frequency response of those. Yeah, I have to go to page 22. Here we go. So this shows H naught, which is the low pass. This shows H1. This is the axis, the frequency axis going omega going from 0 to pi. This is 1, this is 2, H naught, H1, G naught, and G1, all in the Fourier domain. Okay. So so having convinced you that there are some filters that do this, let me now just talk about the three classes of subband filters. So there's three main classes of perfect reconstruction filter families. Okay, and case one that I like to talk about is the most famous one is QMF, quadrature mirror filters. And in these filters, what we have is to achieve aliasing cancellation, which is that term here. Where is it? Which is this term here. To make this whole term equal to 0, people achieve that by imposing the following conditions. By saying that h1 of z is equal to h0 of minus z is equal to minus g1 of z and is equal to g naught of minus c. So all these four quantities, so you're putting constraint on all of these things, and you can show that if you allow that to happen, then you cancel aliasing. So, and this was derived by Esteban et al. In 1976. Sorry. Okay. So essentially, the high pass band, the reason it's called the quadrature mirror filter is that the high pass band is the mirror image of the low pass band in the frequency design, in the frequency domain. So the high pass band is the mirror of the low pass band in frequency domain. And one advantage of having a system like this is what? Instead of having to design 4 filters, now you have to design what? You have to design one filter, right? Because all 4 of, before we had to design H naught, H1, G1, G naught, now we have to design one. And we better design that one. If now that we design one, and from that one we derive these other 4s, we better design that one in order to do what? To achieve perfect reconstruction. In other words, to make this thing equal to be to 2. Okay? So essentially, to achieve, you only need to design one for aliasing cancellation, and then design it in such a way that, so to achieve PR, perfect reconstruction, design that one filter to achieve PR, and the condition then becomes, let's call that the one that we end up designing is just H naught, okay? It becomes H naught squared of z minus H naught squared of minus z is equal to 2. Okay? And just so that you can see what filters, what QMF filters look like, here's an example. If you can switch back to the computer. Hello? Can you switch back to the computer, please? So here's an example of a 16-tab QMF filter. this is an h1 of z that satisfies this condition, and you can see it has this kind of ripples. Okay. Now it might not be possible to satisfy this perfect construction h naught squared of z. We might not be able to satisfy it precisely. Okay. But we can certainly approximate it. Okay. Okay. So the next um, and then of course you can translate these conditions between h naught and h1 into from z domain into the impulse domain. Okay, so let me now move on. So this was QMF filters. I'm now we're going to talk about conjugate quadrature filters. In other words, CQF. That's the second class. And what can we say about those kind of filters where you achieve aliasing a different way by allowing h naught, let's see, h naught of z to be equal um, to g naught of z inverse, which we define by this little function f of z, and then at the same time we're letting h1 of z to be equal to g1 of z inverse, which what we now call that, this is a definition, but we now call that z times f of minus z inverse. Okay, and this result was derived by Smith and Barnwell, both at Georgia Tech. I think Smith has now left Georgia Tech. Is that correct, Sergey?
Elizabeth Smith was Barnwell was still there.
Yeah, Smith. So you didn't overlap with Smith. Smith was there for many years. He's now a dean or chair at Purdue. Do we have anybody from Purdue? No. Anyway, so Smith and Barnwell, 1986. By the way, this guy Smith is a runner, and it's very rare to find like an academic professor type who's also good in athletics. He lit, or he was one of the part of the group that lit the Olympics. Oh, now I have to remember what year. Like 8 years ago or 12 years ago or something like that. In any event, to his credit, he also developed this famous, filters. Okay, so this is conditions under which you achieve aliasing, and in the impulse domain, this kind of ends up being as so in the impulse in this time domain, if you will, we end up having h naught of k is equal to g naught of minus k, which we define as f of k, and then h1 of k is g1 of minus k is equal to minus 1 to the power of k plus 1, f of minus k plus 1. Okay. And so these conditions achieve aliasing. And again, we only have to design one filter, f of z. Once we know what f of z is, all four other filters are known. Okay. And for perfect reconstruction, so to achieve PR, we need to have the following conditions, which is h naught of z times h naught of z inverse plus h naught squared of z minus z, sorry. H naught of minus z inverse has to be equal to 2. Or in the frequency domain, all we have to do is to make sure in the f guy, which is the same as h naught, we have to make sure that h naught of omega squared plus h naught of omega plus pi plus or minus pi squared is equal to 2. Those are all both the same condition. Okay? And finally, I'm going to talk about the third class of subband filters, which are called orthonormal, which is the beginning of what how wavelets were. So a special kind of, so here's the link between subband. Here's how we're going to jump from subband to describe what wavelets is. So if our analysis filter set of filters satisfy the orthonormality condition, then we've designed wavelets. Okay, so a special kind of subband coding, if you will, is wavelets. So class 3 orthonormal and in that case um, we have the following kind of set of conditions, if you will. uh, h naught of z is equal to g naught of z inverse. H1 of z we pick as g1 of z inverse, and then g naught of z, um, sorry, uh, g1 of z we pick as minus z to the power of minus 2k plus 1 g naught of minus z inverse. Okay, where I'll tell you in just a second what the k stands for. Um, is the number of filter taps in each filter. So 2k is the number of filter taps in each filter. And finally, so not only do we have to have these, but to achieve perfect reconstruction, we also have to have g naught of z times g naught of z inverse plus g naught of minus z, g naught of minus z inverse to be equal to 2. So these are all aliasing and perfect reconstruction conditions. Okay. So orthonormal subbands are uh, are essentially the same thing as wavelets. Okay. And in the time domain, so in the same orthonormal filters, in the time domain, what we have essentially is that they're step beyond bi-orthogonal. Remember, bi-orthogonal was equivalent to the condition of this being equal to 2 and this being equal to 0. And all of these things satisfy already bi-orthogonality. But these guys are orthonormal, which means that the inner product between gi of n and gj of n plus 2m is equal to delta of I minus j delta of m. Okay, and and then furthermore, you can show that for orthonormal filters, what we can also show in the time domain is that g1 of n is equal to minus 1 to the n g naught of 2k minus 1 minus n, and hi of n is equal to gi of 2k minus 1 minus n for I equals 0 and 1. So there's a lot of relationship between these various kinds of filters. Okay, so now let me now move in and show you some let me just as an example, let's look at figure 7.6 in um, in Gonzalez and Woods. So bring this down. This is figure 8. Okay. Okay. So if I go back here, so this is the basic subband filter. This is the QMF, CQF, and orthonormal cases. This is how we do subband image coding. So you start with your signal, you pass it through these two filters, you repeat it along the rows, and then you in other words, um, if it is x of m comma n, m is the first index, n is the second index. First you pass it through a one-dimensional subband, one-dimensional filter h naught, and then of m to deal with the rows, and then you pass it after you subsample it, you pass it along. You subsample along the rows, then you pass it through a vertical filter h naught of n, and then you do another subsampling along the columns, and so you end up getting 4 different kind of signals. This is low pass in x and y. This is low pass in one dimension, high in the other, low pass in one dimension, high pass in the other, and this is high pass in both dimensions. Anyway, since we're talking about orthonormal filters, let's not get distracted. So this is an example of Doboshev orthonormal filters, H0, H1, G0, and G1. This is the first set of wavelet filters that was invented. These H0s and H1s and G0 and G1 indeed satisfy the orthonormality condition that we've been talking about here. And they're referred to as Doboshev orthonormal filters. She's a mathematician by training. Actually, in one of the conferences in the late 80s, I was roommates with her. I forgot it was in Eennlb or something like that. Here's a... I'm going to skip a lot of these things. Yeah. And now talk about, how does wavelet transform actually work. So I'm going to... I don't think this guy's going to show any more images. So the way wavelet transform actually works is kind of the following way. You start with a signal, and you pass it through these filters that you've designed. You subsample it. Let's say this is the low-pass filter. Subsample it and get a signal. You pass it through a high-pass filter. This is H0. This is H1. Subsample it. And then, sorry, the high-pass filter you keep. The low-pass filter here, you further decompose it into low-pass, high-pass. I don't think this is the best picture for me to show you. So let me go back to... no, this doesn't have it either. This might have it. Okay, this is a good picture. Excellent. Then I don't have to draw it on the picture. So here's a discrete wavelet transform. So not only these H0, H1s, and G0, G1 satisfy this orthonormality condition we talked about, but typically here's how we do it. You start with your signal. You sample. If it's analog, you sample it, but I don't think we need to worry about that for now. So H0 is your low-pass filter. H1 is the high-pass filter. You subsample that, send it over, upsample, and filter. But for the low-pass signal, because it has a lot of energy, what you end up doing is you, after you downsample it, you repeat that process again. Upsample, downsample, da-da-da-da. And then this signal here, you can again repeat the process again in a nested way so that the low-pass signal keeps getting filtered and processed. Okay? So what is the final picture that you end up getting? For one thing, there's no signal expansion going on, but for another, this is kind of what you get. So if you started with the so this is the Cohen. So depending upon how you design your H0, H1, you could have different classes of different kinds of wavelets. So I already showed you the Dobershire filters, which is this one, 8.8. And then there's Cohen-Doboche Fovio filters, which is 1711. That means the H0 has 17, H1 has 11. This one, H0 and H1 both have 8 and 8. HAR, which is a well-known filter even before Doboche, 2 and 2 taps. And Simlets, which is 8 and 8 taps. But basically, this shows kind of the fundamental basic idea in that you start with a big image. This is the low. You first do a low pass operation, and you have a signal here, and you have 3 high pass signals, and then you get the low pass signal, and then generate the low pass here, high, 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 and then you get that low pass signal, generate the low, high, high, high. Is everybody clear how this works? Let me see if it has, and this shows the Doboche orthonormal 8-tap filters, H0, H1s for it, H0, H1, G0, G1. Further going down, Simlets, H0, H1, G0, G1, and biorthogonal Cohen-Doboche 1711 filters. So I'd like to go to the beginning of this presentation because I think this thing might clear a little bit better as to how wavelet coding works. Just bear with me. Okay, so the switch from 1D to 2D might not have been terribly clear, but here's the idea. This is omega x, this is omega y. So when you do the low component is this gray area that's shown here, then these gray components is high frequency along x, low frequency along y. This one is high frequency along y, high frequency along y, low frequency along x, and these 4 little frequency domain in the frequency domain, this is the region that the high version has. And then what you do is you start with this guy and further decompose it to low, high, low, high, and high, high. Okay, is everybody clear about how this thing is working? And if you do that, then here's an example of a 2D wavelet transform. You start with the Lena image, which we all have seen and know. The first step is just this. You have the Lena here, which is low pass in high and in x and y dimension. This one is low pass in x, high pass in y. This is the other way, and this is high pass in both of them. And then you start from here, from this picture, you then decompose this LL component, low component, further in order to get this picture. These 3 pieces are the same as what they were before, but that big low picture is now has low, high, low, and high again. So this is a 2-level wavelet decomposition. And you can use your favorite wavelet. You can use Dobershire, Cohen-Dobershire, this, that, whatever. It doesn't matter, really. And then further, you can decompose that signal, this signal, again into its low, high, etc. And what you get is something that looks like this. And now, I want to end the lecture. This is the very last thing I want to say. How do you quantize and code these guys? So the famous break, and initially when wavelets introduced, it took 10 years. It took a long time before image processing people figured out how to efficiently quantize and code it. Just uniform quantization, apply Hoffman coding. It doesn't beat DCT. It never did. So this smart guy, Jeremy Shapiro, who actually was classmates with me at MIT, who was at Sarnoff lab when he invented this, came up with this concept of 0 trees. And this is almost at the end of the presentation here. And here's how it works. So the observation this guy made is, if you go back, sorry, let me go back to where we came from. If you go back to this picture, you can see is that for example here, you can see that first of all, these high components have very little energy. So wavelets have achieved one of the things that transform coding, the compactization, right? The number of samples hasn't increased, unlike pyramid coding. It's constant. But the number of pixels with high energy is very few. these signals have almost close to zero energy. But here's the observation Shapiro made, this guy at MIT, who was at Sarnoff when he came out with this, which is if there's a non-zero coefficient at a particular location, it also is non-zero in the other bands, the same corresponding locations. So for example, this location corresponds to this location, corresponds to this location, etc. So there's correlation between non-zero coefficients for these subbands. There's a lot of correlation, and it's that